ready to dive deep into something pretty amazing. We're talking carbon, the element that's not just in your pencils, but in you, in me, like everywhere. And get this, our source material, a 10th standard CBSE chemistry chapter. Who knew textbooks could be so exciting?
What's wild is most of Earth's carbon isn't even, visible. It's locked up in rocks, fossil fuels, leftovers from ancient life. Talk about a blast from the past.
Okay, already mind blown, and we're just getting started. So how does carbon become the, VIP, the backbone of life as we know it?
It's all about those bonds, man. Imagine atoms wanting to hold hands so they don't, freak out. That's covalent bonding, basically, sharing electrons to feel secure. Carbon's got 4 hands available, so it can bond with up to 4 other atoms. Talk about a social butterfly.
It's like carbon's the life of the periodic table party, making connections left and right.
Exactly. And it's not just about who it bonds with, but how. Remember those long chains, branches, even rings in, like organic molecules? That's carbon going all out, thanks to catenation bonding with itself.
Hold on, so not just a social butterfly, carbon's like a master builder too.
You got it. Think of a basic hydrocarbon chain, like a Lego base plate. You can attach all sorts of Lego bricks. Those are the functional groups to add different functions, change things up.
Okay, I'm picturing it. We got our base plate, but what kind of Lego bricks are we talking, and what do they actually do?
Well, we got hydroxyl groups. They give us alcohols. Carboxyl groups make carboxylic acids.
Yeah.
Loads more. These groups are like adding a power up to the carbon chain. Totally change its game.
So the functional groups are what bring the spice to the carbon compound party.
100%. And speaking of different vibes, let's talk allotropes. Carbon's got a whole wardrobe of outfits, each one unique.
Wait, are we talking diamond versus graphite here?
Right.
That's always messed with my head. Same element, but totally different.
You know it. Diamond, those carbon atoms are bonded super tight, 3D network. It's like they're holding on for dear life. Nothing can break them apart. Hence, the crazy hardness.
So diamond's like carbon at its toughest. What about graphite? Soft, slippery.
Right. Graphite's carbon atoms are in layers, like sheets of paper stacked up. Bonds within the layers are strong, but the layers themselves are kind of chill. They can slide around.
Diamond's clinging on, graphite's going with the flow. That's wild how atom arrangement makes such a difference.
And it gets weirder. There's fullerenes. Picture carbon molecules shaped like soccer balls.
There is. Carbon soccer balls. You're kidding. Okay, what do you even do with that?
Fullerenes are pretty new to science, but they're huge in nanotechnology, materials, all that. Could change everything from phones to medicine.
Carbon. Past, present, future. Starting to see why it's such a big deal.
Now we're just scratching the surface. Now that we got the basics, ready to dig into hydrocarbons and functional groups for real.
Absolutely. Let's get into the nuts and bolts of how carbon builds the world around us.
All right, so we've covered carbon's amazing bonding skills, how it builds those chains, rings, all that.
But there's a whole other layer to this.
Literally.
Well, yeah, kind of. We got to talk about hydrocarbons. The excerpt mentions them as the foundation.
Okay, so hydrocarbons, why are they so important? Break it down for us.
Think of them as the bare bones, the starting point in organic chemistry.
Right. They're just hydrogen and carbon, simplest structures you can make. Chains, rings, that's the basic setup.
So it's like plain dough before you make a pizza. The hydrocarbon's the base.
Perfect analogy. And those toppings, that's where functional groups come in, just like we were saying before.
Okay, so they attach onto the hydrocarbon.
Exactly.
That's good.
And bam, suddenly the molecule's got a whole different personality, different chemical properties.
So functional groups are like pepperoni, mushrooms. They decide what kind of pizza we're having.
You got it. Let's say hydroxyl group, for example. That's an oxygen, a hydrogen, buddies, bonded up. Slap that hydroxyl onto a hydrocarbon, boom, you got yourself an alcohol.
Wait, like alcohol?
Right.
As in what we drink?
Yep. Ethanol, the classic. It's a great solvent, dissolves other stuff, super useful. Medicines, perfumes, you name it. But like the excerpt says, you got to be careful with that stuff.
Definitely. Moderation, right? But still, wild how one tiny group changes the whole game for a hydrocarbon.
That's chemistry for ya. Now, swap that hydroxyl for a carboxyl group, which is a carbon double bonded to an oxygen and also bonded to an OH group, and we're talking carboxylic acids.
Carboxylic acids. Those sound kind of hardcore. What's their deal?
Think vinegar, that punch-in-the-face smell, the sourness, that's ethanoic acid. A carboxylic acid doing its thing.
No way. I never would guess.
And it's a natural preservative, too. Pickled stuff. That's our buddy ethanoic acid at work.
So we're talking disinfectants, preserving food, carbon compounds are everywhere. This deep dive is blowing my mind, honestly.
Yeah. We're just getting started, ready to tackle something everyone's dealt with, hard water stains.
Ugh, don't get me started. Bathroom nemesis number one. What's the deal with those, and how does soap even work on them? So, hard water stains, it's like no matter how much you scrub.
Right. Stubborn thing.
What's the science behind that?
Yeah.
And how does soap actually, fight GHD back?
Chemistry showdown. Hard water, you know it. It's loaded with minerals. Calcium, magnesium, they're the usual suspects.
What?
Those guys react with soap and bam, soap scum, the bane of our existence.
So it's those minerals messing with our nice, clean suds.
Pretty much. Now, soap molecules themselves, they're kind of cool.
Yeah.
They got two ends. One's all about that water hydrophilic, fancy word. The other's like, oil and fat, my people. Hydrophobic.
Playing both sides, huh?
Exactly. That's how they surround the dirt, the oil, make these little spheres. Micelles, if you want to get technical.
Cells.
They trap the dirt inside, and because their outside's all water-loving, whoosh, down the drain they go.
So soap's like, come on, dirt. Let's get you out of here.
Exactly. But hard water, that's where things get messy.
Because of those minerals.
Bingo. They mess with the soap molecules, break up the party. No more micelle fun.
Ah, so less lather, more stubborn scum. It all makes sense now.
And that is where detergents strut in. They're like the upgraded soap. Hard water doesn't faze them.
Because they're made differently?
Yep. Different molecules, less reactive to those minerals, cleaning power unleashed.
Detergents.
And
They don't negotiate with hard water stains.
it's all about understanding the chemistry. We've gone from deep earth carbon to, what's in your cleaning cupboard?
This deep dive has been amazing. Who knew a chemistry chapter could be so, I don't know, mind-expanding?
Right. And we've only scratched the surface. It makes you think, though, if carbon can do all this, what else is out there?
Seriously. Okay, that's going to keep me up at night. Maybe a question for another deep dive.
For sure. In the meantime, keep those science questions coming, folks.
From diamonds to soap scum, it's all connected, it's all carbon, and it's all amazing. See you next time.